Okay. Right. Well, I just spent 40 minutes writing this code, and my mic wasn't switched on, so the commentary doesn't exist. So rather than re-record it, I am just going to walk through the code that was written and explain what it does. So what we were doing is we created our simple bitmap storage that implements a bitmap storage protocol. We initialize it with a CG image, etc., etc. So that's the simple. That was the existing one we had. We wanted to make a run length encoded version. Now, to run length encode something, essentially you just count how many pixels of the same color there are, and the count plus the pixel is a run, which I've created this struct for. And basically, this is really good. It's used for compression, but we're not really worried too much about the compression, although it will work pretty good as a compression because of the nature of what we're doing. Because what it's going to do is it'll count how many pixels of a particular color there are in each line, and that's one run, and then it will count another run. You see that's like, and then there's another run here. So that's like 3 runs. As this is just like one run. So that is very much, rather than storing every single pixel in this chunk of thing, we just end up storing single runs for each line. So we're going to get, so it's going to be quite good. It is going to compress it, and that's the original purpose of run length encoding. But then, because we've got these run lengths, so a run length which is, if there's just one run length in the line, then it's a blank. There's no text in it. But if it's like broken up a lot, so it kind of goes yellow, font color, yellow font color, it's very lots and lots of runs because it's so broken up, then that's a really heavy hint that this is some text here is contained within those lines. So I think it's going to be really useful information that we could use to improve the text processing algorithms in Readable. But first of all, we should replace. So what I've done is I've replaced, when we create this is where we create the bitmap from the image that we're handed, and I've replaced the storage with the run length encoded bitmap storage. So I've done that, and then so this implements the protocol, so you can initialize it with an image. Under the hood, it's actually creating a simple bitmap storage version of the bitmap, because it needs to, it's going to need the same, data, so it might as well use the existing bitmap storage. And then what it has to do is and I haven't really worried about optimization yet, and we're going to move on. We'll see why in a sec. So for every line, what we've got is the first run, we initialize the run with the first x, the first pixel at x colon at 0. But there might be more than one run, so we have an array of runs that we're going to create, and we just run through that line with x coordinates 1 to through the width, and if the pixel is the same as the current run's pixel, then we just increment its length. If it's not, then we need to sort of bank that current run create a new run and go back through the loop. So this will collect up however many runs there needs to be. It could be as few as one. So 1 pixel would be a run length of 1 pixel. Of course, it's got an additional amount of storage. But most of the time you're going to have run lengths of 2, 3, 1,000 pixels. So the storage is considerably less, but we also have this interesting information. So here we're going to bank the final run because we've hit the end of the line, and then we're going to put that into our lines. So our lines is an array of arrays of runs. And then I'm going to move to modal first. So to get the kind of most frequent, the mode average of background, hopefully, we do this. So it looks more complex than it is, but basically we're going to sample a number of lines, and we're going to take the whole line now because we've got it in lines, and then we're going to simply, we're going to get random lines, and then we're going to sort each line, which is an array of runs, by run length. And then we're going to take the first, which will be the longest run length. So for each line, we get the most common, the longest run length. That's an interesting one because we should really add them all up together. There's an assumption here. Which I shouldn't really assume, but I think it's okay for now. Assumes I think this will generally work. What we're looking at is, the longest run length. It'll do for now. So if we picked a random, it's interesting actually, we could do something that just takes run lengths of like ones which aren't broken up. Couldn't we? Alright, we've got an assumption here. We'll fix that next time. So we've got these runs, which are the longest runs for each. I still don't like it. I don't think I'm going to take the first. No, we're going to leave it for now. Okay. So we've got pixel counts. So now we're going to count how many particular colour in these longer runs. So we just go through them. If we fill out this dictionary, essentially, that's all that does. Just increments the run length. It defaults to 0, obviously. if it's not in the dictionary, we've got a default value of 0, and then we then put it in the dictionary, and then we're going to get the modal by, again, taking these pixel counts, sorting them by value, and taking the first, and the key is the pixel, and then we're going to return the luma of it. So we could do the same kind of adding everything together, but add all of these as well, which I'm kind of minded to do. So let's see what we can do here. Maybe we get the lines. We don't need them sorted then. I'm not going to sort them. I'm going to do that. Just going to flatten it. Okay, it's better. So flat map is just making my array of runs. We take all the runs, we flatten them into runs, so we can do this. So now, that is definitely the mode. By sampling, so we don't know, we could get really unlucky and sample the worst lines, but it's a huge number of when this max pixels comes in, it's the number of lines in this particular thing is over 2,000, so we're sampling like 210 lines, so it's a lot, so it should be enough. So that's that, so that's the modal luma. And then here is the problem. It works, but it's very, very slow. So in simple bitmap storage, to get the pixel XY was pretty simple. It's just just find the index through simple arithmetic, and then return the index, the indexed pixel, like here. But so that's fast, because it's not as fast as it could be, but it's fast enough. But this has to, because it has to sort of uncompress or decompress as it goes, and when we hit something with a lot of runs in a line, which would be, again, your line with letters would have many, many runs, then this while loop gets really, really slow. So slow, it's actually unusable. But let's have a go. Demonstrate it. Go in the demo. And now, it should be done, but oh no, I'm gonna have to wait and wait and wait. This is because this is just a slow way of indexing an X, because we have to keep going through this while loop. So it's just never going to stop. Right, but this is because now let's put it back to a simple bitmap storage. I'm going to show you how it should have worked. Go here. So we change it back to simple. So it's not as fast as I want it to be, but it's fast enough for now. And as you see, like, it's a lot faster than the other one, which does work. It's just I'm not going to make you watch it because we're going to start trying to fix it instead. So the problem is, we rather naively, I think I said I don't like. Where is it? There's a bit where we make words. Is that it? We're indexing a lot, so we look for where we do this XY. This is in modal colour, which I don't think we use anymore. So we can probably get rid of that. It's in this detect lines thing. What this does, and it's in this modal colour. Don't think we use modal colour. Oh, we do. Interesting. We can probably get rid of that as well. Okay. But it's in this, so what was it? Detect lines. Now, what I've noticed is we're just incrementing x one at a time to get that, and essentially that's all this does. Is it scans the every single pixel in the line. Now, there could be much better ways of doing this, but because we've got a different every time we call this in the run length encoded version, we're in this massively long while statement. But we don't need to be. We can change this to use iterators. Rather than these horrid for loops, we should be using an iterator. We should iterate through. This is essentially just iterating through every single pixel to detect the lines. Okay? So we can set the isId line to be true or false. Okay, so essentially it looks and it says, is this pixel? And then we don't even. Once it's true, you don't need to set it. Like, there's an easy out here actually. First of all, we need to. I mean, this is just horrid code, and this is the problem with for loops. Once we set true, we're done with this line. Yeah. So we should do a break. Doesn't really make that any faster. But it might make the other version faster. No, cool. Okay. So I wonder if this does it in any kind of tolerable timescale. No, still ploughing away. So we believe it's stuck in here somewhere. So this is coming from make lines. Use background. So it's this piece here. Now there's a couple of things here. This X again. We're just going through it. So this needs an iterator. We need to be able to iterate through a run and through an array of runs. And if we do that, then we don't have to do this while loop. So we're going to fix the API for bitmap storage. So we'll leave this in, but we're going to add an additional function, which is going to give me and we're going to take a bitmap storage protocol iterator. So we're going to have That's going to go into bitmap. Tell you what, let's start. Right, if x is less than width, it's called just kind of replace it. Okay. Right, we've made a bitmap storage on the iterator. I'm going to worry about this now. and we're just going to replace part of the for loop with something that uses this iterator. So because we've got this line iterator, essentially initialize it with the bitmap and the y, and then this is the thing that's going to this is going to, every call to next is going to bump x plus 1. We're going to return the bitmap xy. So with that done, we should be able to create an iterator. For each line. So if we go back to finding where this happens in our bitmap, this is it. So instead of this for x loop, we go for create line iterator bit self and y. Delete that. Okay. Iterator to next. Okay. Right. Notes. We get here. We know. Okay. So we've replaced the for with a while. Now this is not going to do anything new here, But because we've now used an iterator, we'll be able to rewrite the iterator in a way that is more optimized for the run length stuff. So let's just check this. First next is going to be just return yes, and then we defer the addition for the next one. So we're fine. So this should actually just do what it used to do with the for loop, and it looks more complex. But we've basically abstracted away the for loop. And we're still using this while loop, which isn't ideal, but because of this, we can these two lines instead of these three replace the for loop. The for loop is just iteration anyway. So that should work the same as before. Let's test it now. Need some automated tests really. I think they're still using the run length encoding. Let's change that to simple. Fingers crossed that will still work. Okay, yeah, fine. Okay, so that will do for this episode. Next episode is going to be, we're going to create a new iterator for the run length encoding, and hopefully that's going to really improve performance. So we took one step back, and now we're trying to refactor the code to move on, I suppose. We've done that with the introduction of this iterator. Alright, that's it.